Now, though, we definitely have a bit of a mystery here, right? We have to really reconcile two very different sets of experimental results about our electron, right? We have this new G.P. Thompson result that is saying that the electron locations, right, the electron events, an observation event for an electron is happening at random locations with probabilities described by wave physics. But we've also seen in very beautiful experiments by the father, J.J. Thomson, that the electron behaves beautiful, perfect classical physics. And we need to see if we can get these two to line up with one another. So just to recall, right, what J.J. Thomson, the type of thing he would see, so this is what J.J. would be seeing, would be, remember, he would take cathode ray tubes and deflect the beams in various ways. So say we are putting our electron through some kind of a deflecting plates, then of course they would bend up this way, right? And the particle just moves along here following a perfect classical trajectory. And as it does that, right, all of the physics that we're used to works. Now, we have to see if there's a way we can begin to reconcile these two pictures. And the way to do that, or the statement that we're trying to do that, is the correspondence principle. We need to find a way where this probability description can line up with this classical particle description. And the basic way of doing that is to say, okay, let's take a particular instant in time t, where my classical particle, I'm expecting it to be here. And what that means really is I expect that if I try to detect the electron, if I try to force an electron event, the location where it occurs should be right at this spot. Now, what we can do is we can imagine maybe we can describe this with a probability, right? But I would need a probability, described somehow using 2214, 2218 ideas, but I want a probability that's kind of localized in some patch very close to my particle. Now, for this to work and truly give correspondence, we will have to be able to, and we'll discuss this as the course goes on, be able to localize this concentrated probability region, right, to a very small area so that you wouldn't really notice any discrepancies. So the idea here is that at time t, the probability of finding the particle at a given location should be concentrated, should be peaked very close to the classical trajectory, what we would expect classically, to the classical expectation. And what that probability then is really describing, as I just said, is the region for potential electron events, for seeing those. Right? There's certain potentiality for electron events to occur, and where they occur, evidently, has to be concentrated near some particular point. And that would be, say, at time t. Now, what we also need to happen, though, is that if we wait to some time t later, this probability region has to have moved. So what we have this picture then is as time goes on, there's a moving probability region, and we want this probability region to be described. We want p of x and t again to be described somehow as the brightness function that we would expect for some kind of classical light wave, right? Classical light. And the first question really is, can we do something like that? Is there even the possibility in descriptions of waves from 2214, 2218, where we could have a wave concentrated in a region and then that region kind of like move along? And yes, in fact, there is a concept exactly like that, right? It's the idea of a wave packet. Now, we've been joking around a little bit earlier on when we were talking about Star Wars, right, and those little energy weapons that send out this beam right? This beam of light that shoots out, right? You can definitely make wave packets that are concentrated in a given region, and then as they move along, this wave packet moves along, the region where there's significant amplitude moves along, which would mean the region of brightness, or the probability region, would be moving along, right? And then that could follow, if we can arrange this somehow, that could follow along always with the classical trajectories, and that would explain why when we go and look for the particle, we always find it very near, so near we wouldn't notice a difference from the classical trajectory. At least so near if it's an extremely, a macroscopic type particle. Now,